we do that loaner program to give people an idea on what's available to them. Well,
Yeah, it
listen,
was awesome. I recommend it.
I'm so glad. All right, let's take a look. I do believe we are recording, and let me make sure.
Yeah, it is. It's recorded.
Okay, so let's move on. Ladies and gentlemen, I'm going to show a screen to you about our upcoming speaker, and then we're going to go on with some announcements. All right, here we go. Take a look. Now, Vincent, I stole this picture of you. It looks like you are out in the mountains looking at the Aurora Borealis. I hope it's all right that I use that as an
That's
image.
fine. Anything online is I mean, fair game, right? It's public
There you
domain.
go.
So
There
yeah.
you go. All right, ladies and gentlemen, take a minute and read what's in store for you this evening as I will stop talking.
Ooh, I see space physics. What he has to explain that, Vincent, when it's your turn, tell us a little bit about what that study is.
Sure. I mean, I can just say it really quick. It's basically astrophysics, but everything inside the solar system. So it's all the stuff. It's all the stuff that people ignore for the most part.
Okay, moving along. All right, a couple announcements. Here's one for everybody, and this is to remind everybody that
Not till the beginning of March, I think.
I'm sorry. Okay, somebody left their microphone on. All right, this announcement basically reminds everybody, last summer, your board of directors came up with the desire to come up with a new logo. We did. This is the new logo that we have, and we actually created a sew on patch that your board of directors has on their uniforms, and we also use it for our Star Tours people, and members can have access to this patch as well as name badges. If you're interested in securing one, let me know. This is our business card, and we use this at all of our events. And some of you who have attended our events see me and see them being dispersed amongst visitors and members. And we do that because we want to make sure that people understand who we are and what we're about. And this says it all. I think we hope that people understand we are not a super scientific organization. We are a hobby. And although we do have some very scientifically oriented members and know what they're doing in reference to the science of astronomy, but this card is available to everybody and anybody who is a member of this organization. And when you come to our events, please ask me for one, and you can share it with your family and friends. Okay, another reminder, if you can
Oh, you want me to listen to with this?
if you can
What are you telling me? Don't make a
mute
face
the
at me.
microphone.
Yes.
I've got somebody with a hot microphone, and it's not helping. I don't know who it is. Richard, can you figure out who it
Yeah,
is?
it's Sue. You can tell because if you can see all the participants,
Oh yeah. All right.
her little box lights up when the noise comes.
All right. I just
There
muted
she
her.
goes. She just muted. We're fine.
Oh, I did. I muted her. All right. Take a look at this slide, ladies and gentlemen. Since 1948, we started over in the area of Phoenix College, 15th Avenue and Thomas, and we've been around the valley since 48. And if you are a newbie and you found out about this lecture this evening and you are not a member, you have access to join our organization by visiting our website at pasaz.org. I don't need to advertise much more than what this slide says. We have monthly lectures like this evening. We have star parties, special events. We have telescope workshops. that are phenomenal, helping people who have been given a telescope, bought a telescope, had a telescope for years, never used it, and then they're breaking it out. These workshops are phenomenal. And a reminder, you'll hear me announce that we're looking for more and more instructors who can help us with the instruction phase of the telescope workshops. Okay. Richard Myers is our editor of our monthly publication known as the PAS Times. This publication is available to everybody, especially members. Members get this mailed to them on a monthly basis. And Richard is reminding all of us, take a look on the left-hand side, he's looking for you as a member to make your contribution to this publication by submitting articles that you wrote or you want to share. You can also provide your perspectives and insights, and of course, your images. If you have some fine images, please share them with Richard Myers at editor@pasaz.org. The organization loves this publication because it is chock full of all kinds of interesting information and links to other organizations that can help you in your pursuit of the fun game of astronomy. Okay? There is a new group in town. All right. There are astronomers, and then there are astrophotographers. Astrophotography. I'll tell you what that means. That means that these are people who love to take pictures of night objects in our cosmos, deep sky objects, you name it. It doesn't matter. It could be the moon, it could be the sun, it could, whatever. They are into imaging. Recently, the board of directors heard from some of you members that you wanted to get together with other people who have the same interests. Could we form a small group within PAS that is sharing knowledge on the how-tos, the tips, the information, the equipment? How do you do this? How do you do that in reference to astro imaging or astrophotography? And the answer is yes. They recently met here in Phoenix on Bell Road on a Monday noontime, I guess, about 2 weeks ago. And wow, we had about 12, 15 people who attended this meeting, and it was the first get together. And guess what? They are excited to continue with this new subgroup within PAS. If you are interested in becoming active as an astrophotographer, learning more about it, then you need to contact editor@pasaz.org. You can sign up there and you will be placed on a mailing list that will identify for you the upcoming events that they will be holding as they get started. In fact, I have something right here for you. These are their upcoming meetings. And I have always suggested to our local members, if you have a cell phone nearby while you're enjoying this lecture this evening, you might want to take it out and take a quick screenshot image of this for your future references on the dates that are listed for the astro imaging group. I'll leave it up for you for a couple more seconds, but as you can see, it's a beginner group and they have some experts within this group, trust me, and they know what they're doing. And I would strongly suggest if this is a topic that you're interested in, boy, oh boy, here's a good way to start. You can save yourself a lot of time. As we all know, many of us, when we first get into astronomy, we're on YouTube watching video after video after video and reading this and reading that. And yet you want to be able to ask questions and talk to people. Well, here's your chance. Astrophotography, a group within pasaz.org. I would suggest that you take a picture of that and use it as a reference. Okay. Vincent Ledvina, the Aurora guy. The Aurora guy, I looked at his website, and ladies and gentlemen, you are going to be, I think, thrilled with what he has to share with you about this phenomenal experience that some of us have seen. I made it up to Churchill, Canada, Vincent, a couple years ago, and I experienced what you chase, as you say in your
Yep.
introductory paragraph, and it was just amazing. I was looking at polar bears, and I look up and oh my gosh, beautiful sky with the multicolors, the greens and the others. Ladies and gentlemen, this man is going to show you some interesting images, but he's going to tell you a lot more about them. I would like to, at this time, remind everybody of the following, and that is online, one of the biggest disasters we have during a Zoom call is if somebody leaves their camera on or if they leave their microphone on and their phone rings, the doorbell rings, the television is too loud, and it's a huge disrespect to our speaker. So I am asking all of you at this point in time to take a look, make sure you are muted on this Zoom call, and please turn off your microphone on your cell phone so it doesn't interfere with our event, and turn off your camera on the Zoom. It's kind of distracting, and I will do the same. Vincent, what I'm going to do now is I am going to stop screen sharing and give you the floor, my friend.
Sure, sounds good.
So here we go, Stu, with a stop screen share.
And
Stu
I got it.
going.
I'll take it away. Thanks for the
Thanks.
intro. Appreciate it. I'm grateful to be here and happy to talk with you all about the Aurora. In terms of logistics here, I guess we can just put all the questions in the chat, and after I'm done, I'll just go ahead and read them off as I see them. So let's do that. The title of my presentation is The Aurora, Nature's Most Spectacular Light Show. Here's the outline for tonight. I'm just going to start off with a really quick introduction of who I am, then I'll get right into the science of space weather and the Aurora. So I'm a PhD student, and this is basically what I study. So, I'm really passionate about this stuff, and, I know a lot of you probably know about the Aurora, but maybe you'll learn something here tonight. And then finally, I'll talk about Aurora photography, especially time-lapse and also real-time video. And then if there's time, I'll do a little bit of show and tell. And, I know that you all are down in Arizona, so the Aurora may not be as relevant to you as it is to me up here in Alaska, but if you want to take a trip like to Churchill, for example, or maybe Fairbanks or Iceland or, somewhere in northern Scandinavia, this talk will definitely help you out and give you some information about, how to best do that and what you're actually looking at when you're up there looking up at the Northern Lights. So people call me the Aurora guy. It's a name that I guess I was given when I was studying at the University of North Dakota. So I got my bachelor's in physics there in 2022. Then I took a gap year and moved up here to Alaska. I started school here in 2023 in the fall. So I'm a second year PhD student studying space physics. So there was a question about what is space physics? Well, it's basically the study of everything in between, the planets, the sort of invisible space that people think, oh yeah, there's nothing in space, right? It's just this empty vacuum. Well, actually, there's a lot going on. There's solar wind, there's radiation, there's all sorts of things. So space physics is kind of the study of all the plasma in the solar system. That includes the sun, our star, that includes Earth's magnetosphere, that includes the ionosphere. So basically everything from the surface, I guess really from the core of the sun down to the Earth, down to about 100 kilometers is what I would consider space physics. I'm a professional Aurora chaser, so I do this basically as much as I can in my free time. I also started an internship at the Aerospace Corporation, so kind of at the same latitude as you guys down in Phoenix or in Arizona. I go down to Los Angeles over the summers and intern down there in El Segundo, and really passionate about a specific sort of subfield of space physics. I guess it's a subfield of all sciences, but citizen science, right? How can the everyday person who's maybe not studying the auroras professionally, how can they make a difference in the field? And so I've also been to Churchill. This was in March of 2022, and I didn't see polar bears in March, but had a really good time. This was, I was taking a gap year from school, just wanted to kind of kick back and just really hone my skills. So I went up to Churchill with a bunch of friends. I went back in September of the same year, so saw lots of polar bears. That's a good time to see polar bears and auroras. And here's another crazy adventure. I went up to Fort Yukon, Alaska in March of 2022 to help out with a sounding rocket campaign called LAMP. It's an acronym. It stands for Lost Through Auroral Microburst Pulsations. And I actually just came back from Venati, Alaska. So You heard that, the flight schedules in Alaska are kind of weird. I was coming back from Vincent yesterday, and I had already had 2 days where my flights were canceled. So wasn't sure if I was actually going to make it back tonight, but I made it back yesterday, thankfully. Didn't have another cancellation, but that was above the Arctic Circle, a little village of about 160 people. No running water, no internet or cell service. And I was up there assisting with one of these sounding rocket campaigns. So there were two, and I was running a bunch of cameras up there. So let's dive right in. What is space weather? So space weather refers to conditions around a star like our sun and its interplanetary space that may affect space and ground-based assets as well as human life. I think we're getting a little bit of hot miking from Gary's iPhone. But really, space weather is the aurora. I like to say, if you don't know what space weather is, just look up at the night sky, under the auroral oval, look at the aurora, and that's space weather in action. It really is sort of the final step in this entire, link from the sun to the earth. All this energy flowing from the sun to the earth eventually gets dumped into the aurora, and we see that as a result. It's kind of like, we see the aurora and we can see the earth protecting us from the sun and the solar wind and space weather. It's a lot more than that, of course. It's not just the aurora, it's solar flares, it's coronal mass ejections, big shock waves in space. You have plasma traveling at millions of miles per hour. These explosions on the sun release the energy of billions of nuclear bombs in the matter of seconds. You're dealing with million-degree plasmas. You have spacecraft traveling at hundreds of thousands of miles an hour, Parker Solar Probe around the sun. It's a really diverse field, full of a lot of really interesting phenomena, but it does not get sort of the news coverage that regular astrophysics does with James Webb and all the pretty pictures of nebulas and the Milky Way that we see. So yet it has a real effect on humanity and potentially on the daily lives of everyone here in this Zoom call. And it all starts with the sun. So just like we have weather here on the ground, on Earth, we have clouds, we have rain, wind, storms, etc. The sun also creates weather in space. And it gives us warmth and life, of course. It's the reason why we're all here. But it's constantly changing. It's dynamic. Every minute, hour, and day, something is going on. You look up at the sky, you see the sun. It's just this white sort of ball of light that we're not supposed to look at. But when you peel back the layers, which we'll see in a little bit, there's a lot going on in the sun's atmosphere that gives us space weather. And part of the space weather is a wind that constantly blows out from the sun's atmosphere, which we call the solar wind. So imagine like a hot cup of coffee and you have the steam coming off of that, top, just radiating out into your room. Well, it's kind of similar to that, right? The sun is this hot ball of burning gas and plasma, and it's sort of shedding its atmosphere out into the solar system in the form of the solar wind. And it's not just wind, it's charged particles with magnetic fields, and it bathes everything in the solar system in this energy. And usually this wind is calm and gentle, but sometimes it can become strong and fierce, which we'll learn about later. Those are solar storms. And, like I said, space around the planets.
Zoom meeting until I got there.
Zoom meeting.
Zoom, ZOOM. Wasn't what I didn't read it close enough.
Could somebody mute Gary?
I've messaged him. I'm trying to reach out to him, but apparently he wasn't watching.
Okay,
Yeah,
that's fine. I'll just keep going.
Gary there who needs to mute his phone. It says Gary's iPhone.
Yeah.
If you could mute your mic in Zoom, that would be appreciated. Thanks.
I'll just keep going. So, like I said, the sun is dynamic. It's not just this white ball of gas. It's not just this white ball of light in the sky, which we see, traveling across during the day, rising and setting, every 24 hours. When you actually look with special telescopes in space that are able to see extreme ultraviolet wavelengths, you can start seeing the influence of the sun's magnetic fields, which control a lot of the plasma in the sun's atmosphere. So what you're seeing here are different wavelengths of light that would otherwise be blocked by the Earth's atmosphere. So like this one, if I pause it real quick, this is 17.1 nanometers or 171 angstroms. This is the Solar Dynamics Observatory Atmospheric Imaging Array. That's the instrument, and you're seeing these bright regions. These are what are called active regions. They form above sunspots, areas of basically really strong magnetic fields. and these magnetic fields trap plasma and heat them up, which is why the image looks brighter. But you can see, I mean, there's lots going on. There's these plasma prominences that are suspended in the sun's atmosphere, kind of a perfect balance of magnetic and gravitational forces. You have big loops of plasma here connecting different active regions, big explosions, this coronal mass ejection coming off of a filament here. So it's just kind of all goes to show you that the sun is really dynamic, and there is definitely a space weather going on. There's a solar wind that's constantly flowing out, but it is full of these transient events, which we have to watch. Just like, in Phoenix, it might be bright and sunny, 72 to 75 degrees or something for 2 weeks straight, but all of a sudden you might get this huge monsoon or big thunderstorm that might roll in. That's the part of the weather. And so where does all this energy go? It flows out into the solar system, but it doesn't just travel right to the ground here on Earth. Earth has a magnetic field which is generated with in basically interaction with our molten and solid core. That magnetic field is about the strength of a fridge magnet, and it doesn't just stop at the surface. It extends into the atmosphere, out into outer space. So it basically protects us in this little bubble, which we call the magnetosphere. And it would normally be like a perfect dipole, like if you've ever done that experiment in grade school where you take the bar magnet, put the paper on top, sprinkle the iron filings. That's what it would normally look like. But in space, we have the solar wind constantly buffeting our planet, and it creates like this tadpole shape with an extended tail, which we call the magnetotail. This energy, through a really complex interaction, is funneled over sort of the weak points of our magnetosphere, which are above and below over Earth's poles, specifically the geomagnetic poles, and all that energy funnels down over the poles into the polar regions. Particles travel along magnetic field lines, collide with gases in our upper atmosphere, and create light, which we perceive as the aurora. And this layer of the atmosphere is much higher than planes fly. You can see here on the right this diagram, obviously increasing in altitude as you go up. We're talking about layers of the atmosphere, actually quite a broad range, primarily in the ionospheric E layer, but also in the thermosphere. Just generally, this is kind of the region of the atmosphere we're talking about. Basically anywhere from 100 kilometers up to even 500 to 1,000 kilometers. So I'm sure a lot of you are familiar with this if you're ham radio operators, these different ionospheric layers. Most of the aurora occurs sort of in this 90 kilometer to 140 kilometer range. So it just kind of is meant to tell you that, a lot of people think, okay, yeah, the auroras happen. I'm just going to go to the Arctic Circle or, go to Alaska for a day and I'm going to see them. Well, no, I mean, the clouds, if there's clouds, just like, if you're trying to observe the Milky Way, if there's clouds, you're pretty much out of luck. You can see the clouds glowing if there's a really bright aurora, but all this occurs above the terrestrial weather that we have here on the ground in the troposphere. And the auroras actually form via chemical reactions. So you have charged particles raining down on us, so precipitation from outer space, guided by Earth's magnetic fields, like surfers riding waves is kind of how I like to put it. And these particles come down and eventually they start running into more and more gas. It's kind of like a game of Plinko. They keep bouncing around all these gas molecules and gas atoms. There's nitrogen, there's oxygen, and eventually they run out of energy and they just fizzle out. So none of them actually make it really below 60 miles or around 100 kilometers, definitely not to the ground. But depending on the species of molecule or atom that these charged particles from space collide with, you get different colors. So you can see here on the right, these different colors. You have purple, sort of this purple pink, which is at the very bottom. That's formed by the highest energy particles coming from outer space. Of course, if you have higher energy, you're able to penetrate farther down into the atmosphere. This is diatomic nitrogen, so N2. And as you go higher and higher in altitude, actually the gas molecules start to dissociate. So instead of N2, now you just have atomic nitrogen, or you have ionic species like N2 plus, or you have atomic oxygen. So not the stuff that we breathe, but you have N2 plus and you have oxygen at sort of these middle altitudes, which creates a green emission. And then above that, you have oxygen just by itself, which creates red. So that's how you get the different colors. And then by mixing of those colors, you can basically get every single color in the rainbow. So if you've ever seen like yellow aurora or orange aurora, blue, all these different colors, purple, pink, what have you, a lot of that's formed by mixing of these primary colors. I should also say that this blue nitrogen emission You can actually get that at higher altitudes, and that is a real emission. It's just that normally it's sort of found with the oxygen that creates the green light, and it's quenched by the oxygen emission. So we don't see the blue necessarily. But if it's a really strong storm, you get a lot of particles raining down. It can kind of kick up these nitrogen molecules to higher altitudes, and that emission can persist for longer times. So the actual process, if you're confused at this point, like what is going on with all this chemistry, it's really the same process by which a neon lamp lights up, except for our electricity comes from outer space and is energized by Earth's magnetic fields versus from the wall. So I always like to say the aurora is like a giant neon lamp in the sky. And these are some quote unquote rare auroral colors that I've seen. The greens are the most common. You'll see that almost all the time, but you can get these really cool, kind of red, pink auroral arcs. The red's above the green, really prominent in this photo. And then this is right after sunset. You can often get more blue color right after sunset because the sun is also ionizing radiation. So it can sort of energize these nitrogen molecules and produce blue light, which then mixes with the red and creates this purple. So these are sort of rare because the conditions which create them have to be just right, where you get, for example, you don't have any green in this arc at all, which means that the particles are really low energy. They're not making it very far down in the atmosphere. They're not able to get to that green layer. So this is a really interesting arc. And then this is during an auroral substorm, which I'll talk about later, where you have just so many particles coming in, not only more green, particles that can make it down to the green layer, but also more low energy particles. So you just have the entire sort of auroral arc from top to bottom energized with more colors. So there was a comment earlier before we started about the aurora australis and aurora borealis. So borealis is in the northern hemisphere and australis is in the southern hemisphere. We have two auroral ovals where auroras can be seen every single day, as long as it's, I guess, dark and clear. And we get these two auroral ovals because we have Earth's magnetic field lines converging over the poles, right? That's where these magnetic field lines from outer space, if you think of the dipole, you think of the magnet, you have, magnetic field lines coming out of the South Pole and then wrapping around back into the North Pole. If you have a lot of energy, it's all funneled over those poles, and it creates these rings of aurora, which always exist. So here in Alaska, we're certainly underneath one of those auroral ovals because I can see the aurora from my front door every single night, which is pretty amazing. And the aurora borealis and aurora australis, there's actually not a whole lot that's different about them. In fact, even down to the moment where you have substorms in the northern hemisphere, you'll often see substorms in the southern hemisphere at the exact same time. So there are differences between the two hemispheres, and that's actually one of the subjects in our field of auroral physics is interhemispherical asymmetries, which just means what are the differences between the two auroral ovals at the same time. So sometimes you might see an auroral substorm start in the northern hemisphere and then not start until later in the southern hemisphere. That can be because of a lot of different factors. One of the biggest is because the seasonality is different in the northern hemisphere and the southern hemisphere. So of course it's winter here in the northern hemisphere, and the southern hemisphere it's summer. So that changes the conductivity of the atmosphere and can change how the auroras react to that. So speaking about substorms, what are these guys? I actually just wrote a blog article on substorms. So if you go to my website, it's either myfirstlastname.com or theauroraguy.com. You'll see it sprinkled out. It's actually just at the bottom here on my slide. I'm going to play this movie and you'll see this is an all sky camera. So it's a 180-degree field of view. The aurora here is actually pretty bright, but you'll see all of a sudden things get really wild and there's just a big quote unquote explosion of right there. Big explosion of aurora. Now, what is that, right? And if you've ever been to the Arctic, if you've ever seen the aurora underneath the auroral oval, you'll know that sometimes the aurora doesn't look like anything. It's pretty much dim, and then all of a sudden things just go crazy. It starts dancing all across the sky. It's super bright. You can start to see the colors. That's when you want to take out your phone, start taking videos and photos. People are screaming. That's the expansion phase of the substorm. So over the course of the night, the aurora kind of goes through this life cycle where it grows, the energy builds. All of a sudden, there's an onset. It's kind of like you're taking a slingshot and you're releasing it. All the particles get slammed into Earth's magnetic fields, and they funnel over the poles, and then the aurora ovals light up in this auroral expansion phase, this substorm expansion, and then things have to quiet down, and the auroras have to recharge. So this cycle, this substorm cycle, happens around 1 to 2 times per night. So if you think of a night as roughly 12 hours, about 4 times 4 to 5 times in a 24-hour period. And it's a fundamental process of sort of the aurora and Earth's magnetic fields and this whole sun-Earth connection. And it's something that most people don't know because they just go up to the Arctic and they say, oh my gosh, the aurora is crazy right now. And then it dies off and then they are out there for 3 or 4 more hours. But little do they know that that's a recovery phase. Nothing's going to happen for the next, however long. So, knowing about this is really nice because it tells you when you should keep staying out, keep sticking it out in the cold because you're seeing a growth phase. You know that something's about to happen. And then once you see that big burst of aurora, you can kind of go inside, maybe take a nap, make another cup of coffee, or just go to bed because you know that you've already seen, the best show or one of the best shows of the night so far. And so these are mostly high latitude phenomena, but of course the auroras are not just seen underneath the auroral ovals at high latitudes. Those auroral ovals can expand down to lower latitudes, and places like even Arizona can get auroras. So, how can space weather cause auroras in Minnesota? That's actually where I'm from originally. Minnesota or Michigan or Wisconsin or even Arizona. Well, the sun can quote unquote get angry. This solar wind that I was talking about, it really is the sort of vehicle by which all this energy is transported, but it's not just a gentle stream, not a gentle breeze of charged particles. Sometimes you get these big gusts of solar wind called coronal mass ejections, like sun burps or sneezes, where big explosions of plasma are basically launched into space. It's almost like a cannon firing off a cannonball, and if it's directed in Earth's direction, it can get to us. It can slam into Earth's magnetic shield, kind of rattle around. That energy can flow in and down into the aurora ovals and cause them to expand. So these CMEs can cause what are called geomagnetic storms. And we can predict these, but it's really hard. And thankfully, we have NOAA, we have the NOAA Space Weather Prediction Center, who model these eruptions and release, bulletins and watches and warnings about geomagnetic storms that are coming up. There's also people online, including myself, but also one of my friends, Dr. Tamitha Scove. Again, if you're a ham, you're probably familiar with her. She does a lot of sort of live briefings of space weather and actually has a really good focus on the ham radio community and how propagation is going on a day-to-day basis and things like that. So we have people in the community on social media that are constantly monitoring the official government forecasts and sort of translating that down to a more digestible level for somebody. Like, if I asked somebody on the street about CMEs, they're probably not going to know what I'm talking about. So it's really nice that we have these people in the community that are willing to put in the time and sort of make sense of all this stuff going on. But, we can predict these solar storms, but there's a lot of inaccuracy just from the way, we don't have a lot of measurements, right? We only have a couple satellites at Earth looking at the sun, and we can see these things blowing off, and then we have to run them through really fancy models, which make a lot of assumptions that tell us where they're going to go and when they're going to impact Earth, if at all. So it's really hard. It's like, you have a hurricane forming on the western coast of Africa. You take an image of it, and then you have to predict where it's going to fall in the US, right? Without any sort of in-between images. It's really hard. That's basically what it is. And, you may have heard about something called the solar cycle. We're in solar maximum right now. So, we have a lot of activity. We have more active regions, which are sources of these coronal mass ejections. What you're seeing here is a graph of sunspot number versus time. So you can see that there's this nice sine wave, this nice cycle. This is called the solar cycle. So every 11 years, we roughly see a sunspot maximum during solar maximum. And that's when we get all this space weather activity, these big coronal mass ejections that can drive the aurora down to mid-latitude. So, the auroral ovals are always there. Even at solar minimum, if we have no sunspots, there's always solar wind coming out of the sun. We also have coronal holes, which can give us aurora at or kind of minor geomagnetic storms during solar minimum. But during solar max, and especially on the descending phase, we have a lot of auroral activity and we get a lot of space weather. So 2025 should be even better than 2024. We'll have to see. 2024 was pretty good. Best aurora in 20 years by all of the statistics. So we'll just have to see what happens. But if you're into Northern Lights, you're into the aurora, this is a good time. So hopefully you all are ready. And we can predict the aurora, but of course, like anything, it's hard, right? It's not, if you think terrestrial weather is hard, space weather is like 10 times harder. In fact, a lot of people in the field say that space weather is where terrestrial weather was at in the 1960s. It's about kind of the knowledge that we have and the capabilities we have is what we had in the 1960s for forecasting things like thunderstorms or, frontal movements and things like that. So the most common, sort of number that people look at when they think about the aurora and how strong it is something called the KP index. It stands for K-planetary index. It's measured on a scale from 1 to 9. 1 means quiet, 9 is an extreme geomagnetic storm. So after KP level 5 is when we get a minor geomagnetic storm, then it goes minor, moderate, strong, severe, and then extreme at KP 9. Now KP, in my opinion, is very problematic, especially if you're going to high latitudes underneath the auroral oval, because it's a global average of geomagnetic activity every 3 hours. So you get one number every 3 hours. And if you remember the slide about substorms, right, these are little bursts of activity every 15 to 30 minutes. So KP cannot detect substorms at all. And in fact, what's better than KP is webcams, social media, online sites like aurorasource.org. Now, of course, if you're in Arizona, I'm kind of doing this presentation for those of you maybe planning a trip to Alaska, but also those of you who want to catch the auroras down where you're located. If you live in Arizona, it's a pretty slim chance you're going to see anything at a KP 1, 2, 3, or 4, right? At some point, the KP does start to pick up on the activity, just like if you're looking at the stock market, right? You look at the Dow Jones Industrial Average. If that's going up 10%, all the rest of the stocks are going to go up too, right? So at some point, the KP index does start to kind of track the general trend. Obviously, if it's a KP 9, you're probably going to see something in Arizona. You don't have to look at anything else. But if you're going up to Alaska, just don't even look at the KP. It does not matter. Webcams are my favorite resources. This is one that it's allsky.gi.alaska.edu. It's a webcam located up here in Fairbanks, or relatively closely to Fairbanks. There's a lot of other tools too. I'm going to go over all these, but it's going to be pretty fast. So if you have any specific questions, feel free to ask me after. Otherwise, a lot of this info is on my site already about how to use all these tools. But one really popular model, which we use to forecast the solar wind, is called ENLIL, E-N-L-I-L. And that's where you can drop in a CME and watch it spread out through the solar system. So you can see here in this animation, there's a top-down view here. So the sun's at the center, Earth is this little yellow dot, and you're seeing this big kind of banana-shaped, like space croissant is what I like to call it, just kind of enveloping the entire solar system. It's one of these coronal mass ejections, just spewing out of the sun and spreading out throughout the solar system. So we can see these CMEs happen, and we can see them being thrown off the sun. Then we can say, okay, well, it's going this fast, it's going in this direction. Let's throw it into this model, figure out when it's going to impact Earth. So this is a really good model to watch. NASA and NOAA both output these models, and you can see when CMEs may impact Earth. There's also this CME model called HUXT. It's one that I've been using more lately. What's nice about this one is that it gives you all the CMEs. So sometimes there's a lot of CMEs at once, right? During solar max, we're just getting eruptions after eruptions from all these active regions. It can get really busy and messy. So what's nice is it breaks it down into all the CMEs that are coming, and then also gives you a percentage, hit chance, basically. How confident are the models that something's going to arrive? So like, for example, you might see a really great CME. It looks really fast. Maybe it's, coming at Earth, but it's kind of a side swipe. It's not directly aimed, and maybe it only gets a 5% chance of impacting. So, in my opinion, like if I was in, Arizona, I would not be watching that one. I might watch one of these that looks really good, like 100%, right? So yeah, KP index, I already mentioned, it's a global average of geomagnetic activity. Here, actually, where all the observatories are located. So this sort of gray shaded region here over Alaska, northern Canada, Siberia, that's the auroral oval. And then you have the KP index observatories, which are located equatorward of that. So it doesn't even measure the activity underneath the aurora at all. So again, a lot of things rely on the KP index, but I don't believe it's really a great tool to use if you're trying to forecast the aurora in real time, especially if you're in the Arctic. This is just a little funny thing. You go to Chena Hot Springs, which is this place near Fairbanks. It's really, really popular amongst tourists, and they'll post that. Now they don't even say KP index, they just say Aurora power, right? I mean, it's really diluted down at this point, but yeah, they have it on a whiteboard here. Hotels will have it here in Fairbanks, because it's easy, right? Higher number equals better. So yeah, I already mentioned all this. The AE index is a little bit better than KP. It's still a global average, but instead of that magnetometer chain at mid latitudes, now we're moving it up actually underneath the auroral oval. So it's nice because you see a big spike in the graph, the aurora responds more or less the same. So higher equals better. And that's really nice for people because you don't have to worry about, necessarily the science going on. You just look at the number. Is it above 500? Is it above 1,000? You know, in the case for Arizona, I would say probably anything above 1,500 to 2,000. I mean, it has to be pretty high, is what I would watch for, you know, potential, you know, horizon glow at your latitude down there. Real-time solar wind, magnetic fields are, you know, of course, in 3D space, so we can measure them with a coordinate system, right? An X and a Y and a Z. If you're, you know, if you've ever done a physics class, you know the right-hand rule, the physics gain sign. And you can see here, the BZ is the one that's pointing kind of up and down. Earth's magnetic field flows from south to north, so that points north. If the BZ and the solar wind is pointed south, you bring those two together, it's like putting two opposite ends of a bar magnet together. There's an attraction, there's energy that can transfer. So that's why when people talk about the BZ, they're always looking for the south, for BZ to go negative, because that's what allows the energy to sort of penetrate our magnetic shield and flow down into the aurora. It can actually lead to the charging up of these substorms in the growth phase. So just a shameless plug here, I have this ebook. It's completely free. It's like 64 pages. I believe that I just wrote in my free time just to help people and kind of break down a lot of these scientific concepts. So of course, this lecture is recorded, so you can always go back to this as a resource, but I have this ebook on my site. Scan the QR code if you would like, or you can just go to my site and check it out. So the Ovation Prime model, if you're not, you know, not super keen on studying the solar wind and how all that works, well, luckily there's a model that basically takes everything that's going on in the solar wind, puts it through a fancy equation and says, here's what the aurora oval should look like. So it's measured in power in gigawatts. Yes, there's actually that much energy in the upper atmosphere. We cannot harness it. There have been attempts. So people have asked me that before. NASA has tried. So you can see, you know, during really intense activity, you get a huge aurora oval. Of course, this is not real life. It's just a model based on like statistical sort of, you know, the average, right? Like if you have a really good solar wind, what's sort of what we should expect in the aurora oval based on all the historical measurements we have. So it cannot do substorms. It's not, you know, real life, right? If you see a, you know, a 50% chance of a thunderstorm and you see that like, you know, forecast radar on the news for like 2 days in advance, obviously that's not actually going to be what it is. It's just, you know, trying its best basically. So the main thing about Ovation is that, you know, it outputs this probability of aurora in percentage, right? So green is like 10%, red is 90%. You can see the aurora, by the way, this is just the aurora oval. So the aurora is really tall. It's like 500 kilometers, maybe even 1,000 kilometers tall when it's really active. You can see that from hundreds of miles away. So just because there's a big donut here and you think, oh, I'm down in Arizona or Texas or New Mexico, I can't see anything. That aurora, when it's in that substorm expansion phase, is huge. You can see that just like you can see a thunderstorm, you know, way off in the distance. It's not overhead, right? But that thundercloud is so big, you can see it, you know, on the horizon from hundreds of miles away. It's the same thing with the aurora. So, but a lot of apps will say, I have a, you know, you have a percent chance, like a 2% chance of seeing the aurora right now from your location. It's just taking this model and it's, you know, taking this color bar and it's converting that to a number. So that's how that works. Auroral substorms and how to forecast them. I just wrote a blog, so I'm not going to really spend a whole lot of time on this, and I want to save time for other things. So, you know, again, it's sort of this rubber band analogy. You have, you know, energy that grows over the course of an hour or two. It all releases suddenly. You get this big flare up of aurora, and then things have to calm down. So you can actually time these substorms with the GOES magnetometers. Again, this is more of an advanced concept, but if you're interested, I can go over this more after the lecture if you have any questions. But essentially, this measures how charged up Earth's magnetosphere is. So how much energy is sort of waiting in the wings to be released into the aurora. So as the night goes on, you'll see that graph plummet. That means that Earth's magnetic field is getting more stretched out, like that stretched out rubber band. You know, imagine you're a little kid, right? You have a big, you know, whatever sticks and stones you put in this like little slingshot. It's like aurora particles. The actual magnetic field of Earth stretches out and then eventually is released. And you can actually measure that release and see that release in this plot here, this GOES magnetometer with these big spikes. It's really cool. And ground truth data are the most accurate of all, right? Everything I've been talking about so far is proxy, right? You see something in a graph, you infer what it will do with the aurora. So what's the best ground truth data? Well, it's you. And you can track these reports of the aurora on a website called Aurorasaurus. And I actually interned for them. They're a NASA citizen science project. I interned for them back in 2020. It's great. You can go to aurorasaurus.org, and especially if there's a really big storm, you start to see thousands of aurora reports lighting up all over the world with people saying, yes, I can see the aurora, and they attach a photo, or no, I cannot see the aurora because maybe it's cloudy or maybe the activity has died down. So this is kind of fun to watch. If there's enough people reporting, you can even see these substorms in real time. You can see all the reports just kind of move equatorward, like boom, right? As soon as that substorm flares up, the aurora gets brighter, people from further away can start to see it. And there's webcams as well. Just within the last 5 years, these, security cameras that you might have, in your doorbell, like these Ring cameras or these Wise cameras. Wise is a really popular brand. They're sensitive enough in low light that they can start to see the aurora, and it's really, really great. So, these cameras, these light-sensitive cameras, have become a lot lower cost, and now people are running them as aurora webcams. So, I had this big list on my site, and this I thought was really cool. There was a big KP8, so severe geomagnetic storm, last year on October 10th through 11th. There was aurora seen in almost every single state. I think the only state that didn't see it was Hawaii. So Arizona definitely saw it down to the Mexican border there. It was visible, but I thought this was kind of cool because there was this webcam in Maine seeing the aurora to the south. There was this webcam in Georgia seeing the aurora to the north. So that auroral oval, which is usually over like Canada, like kind of the Hudson Bay area, was all the way over the lower 48, which was just crazy. And all these aurora forecasts are sort of, released, or you can look at them on different timescales. Just like you can look at, weather models and see a 14-day outlook. You can look at a 27-day KP forecast, but that's not very accurate, right? As soon as you get on a shorter and shorter range, it starts to get more and more realistic. So, if you're underneath the auroral oval, you're trying to figure out what's going on with the aurora that night, I would start to look at solar wind. I would start to look at webcams, Ovation Prime. That'll kind of give you a 30 to 60 minutes heads up. If you know what the substorm is doing, if you can see, the certain phases going on, that can also give you a heads up of what the aurora may do after. But if you're trying to predict these solar storms, usually you only have about a 1 to 3 day forecast. And of course, there's all sorts of different ways that these forecasts get implemented, in the news and on apps and things like that. So this is sort of my high latitude aurora chasing workflow. First of all, is it going to be cloudy? If it's going to be like tonight, there's freezing fog here in Fairbanks. It's, about 5 degrees. I'm not going to be going out. Like there's zero chance of me seeing anything. So that's the first thing. I already tonight said no. Solar wind looked good. I just like to see what the general state of things is. You can start to see this activity in the solar wind. Like if the BZ is really south, okay, great. Like I'm going to, pay more attention then. Is the GOES magnetometer charging up? How much energy is kind of in the magnetosphere? What does the aurora actually look like? What are the webcams showing? And then I'll just go out and wait. And that's kind of my workflow for high latitudes. It's really simple. If you don't know anything about the aurora, you can pretty much, if you're just willing to stay up, you'll see something. And that's kind of what I tell people. Now, at mid latitudes, it's a little bit more tricky because you have to forecast this activity, right? You're not going to see the aurora all the time. You have to have some sort of geomagnetic storm that's going to come in and shake things up. So essentially, it's everything that I just said, but you're adding this space weather is a space weather coming box right to the beginning. So you kind of look at a bunch of different data and figure out sort of, is there this big solar storm coming? And then, if there's a KP8 forecast that are predicted, right? I mean, that just tells you that, something is coming, right? Even if you don't know what it is, it sort of tells you to start paying attention. And so for Arizona, actually, this is, these are both photos from last year. So hopefully you all saw these. It's possible to see northern lights on the horizon in Arizona, especially if there's a really strong substorm up to the north. And also there's this really cool phenomenon called SAR arc, stable auroral red arc. It forms, it's kind of like a separate band of aurora. So you have your main auroral oval, then you kind of get this like, equatorward arc that forms during big geomagnetic storms, which is purely red. And you can see them with your eye, but they're best seen on a camera. And this is a photo from my friend Alan Dyer, a 360-degree panorama of one of these SAR arcs in Arizona. So this would have been overhead. So now for some tips and tricks, remember, just to back up, if you think all this is really complicated, everyone can do it, actually. All it takes is just a love for the night sky and some patience. It's all it takes. And we were just talking about dark skies earlier before I started. Really helps to be somewhere that's sort of a Bortle 1 to 4. I'm sure all of you are familiar with the Bortle scale. I just went to the site lightpollutionmap.info. It's my light pollution map of choice, and plugged in Arizona, and I found some different examples here. Of course, if you're downtown Phoenix, and I've been to Phoenix and Tempe before, it's pretty bright. So chances are you're not going to see the aurora from downtown Phoenix. But if you went somewhere just out of town, especially, you know, to the east and west or to the north, you don't want to go south of Phoenix, right? Because you're going to be looking back into Phoenix. That's not going to work. So I know for the Milky Way, right, you usually look east or south or west. Well, the aurora is most likely, unless we get like some huge Carrington event, going to be to the north in Arizona. So you want to go north of Phoenix or somewhere to the east and west, and not looking into, you know, a big city somewhere off in the distance. So these are just some examples, right? I mean, I don't know specifically, you know, which cities are the best, but obviously the Grand Canyon looks pretty good. And also you get a little bit further north too. So if you're under high latitudes, you know, the aurora is going to look pretty different. It's going to evolve over the course of the night as the substorm cycle progresses. It might look like nothing. It might just look like glowing clouds. So it really helps to take out your iPhone or your phone and just, you know, take a photo. Your phone's going to see more than your eyes can. So you start to see the greens there. And then, you know, as the substorm expansion phase, you know, occurs, this onset, the aurora can just completely evolve and change into just, you know, spectacular shapes like this spiral, which I affectionately call the Aurora cinnamon roll. Yeah, red glow is really common, especially at lower latitudes. It's just because of the curvature of the Earth. You're looking at the tops of the aurora, so it is green underneath there. It's just that the curvature of the Earth is blocking you from seeing that. So actually, I saw the aurora very, very faintly in India, of all places in India. Now, for context, geomagnetically, that's about the same latitude as Puerto Rico. In India, in the Himalayas on May 10th. So pretty crazy. And this was right in town. I mean, you can see all the light. This is from the city, all this sort of light. There was no moon. It was just that bright, really bad light pollution. But, you know, it's at almost 12,000 feet in the Himalayas. So the sky was super clear and the light pollution doesn't really disperse all that much. So yeah, I mean, this is with some editing. It's a pretty bad aurora photo, but I was proud of it because I saw the aurora from frickin' India. It was crazy. And your eyes see the aurora a lot differently than your cameras can. Obviously, our eyes are not made of pixels. We have rods and cones. Our rods are the light sensitive, cells in our eyes that are always on, always activated. But our cones are the ones that see color, but they turn off if it's too dark. So when the aurora is really bright, it'll start to activate your cones again. You can start to see the colors. But usually at night, there's not enough light to do that, even in a really dim aurora. So you won't see any color in the aurora, but the cameras don't have that limitation. If there's just a little bit of color, it can pick that up. And there's different ways you can kind of biohack, your body basically to see more color. You can just shine a quick, shine a flashlight quickly in your eye. You can start to see more colors in the aurora that way. That just kind of activates your cones for a little bit. They take like 5 to 10 seconds to turn off. So if you, obviously you're going to ruin your night vision. So don't do this unless you're committed, right? Quickly shine a flashlight into your eyes, look away at the aurora, and you can start to see the colors. You can actually see, even if it's a really dim aurora, you can see the colors. And if you cannot see this, I'm not going to tell you what it is, this thing in this gray circle here, then you actually have minor color blindness and you may not be able to see colors in the aurora. So if you cannot see this, this is just a normal color blindness test. I just took it right from the internet. I didn't doctor this up, and there is something in there. If you cannot see that green shape, you do have color blindness to some degree, because it is there. And actually, a lot of people, yell at me basically on social media because they say, "Oh, you're, saturating your images." I've never seen the colors in the aurora like that. And I tell them, I'm like, look at this photo, like, look at this color blindness test. And half the time people say, "Oh, I can't even see that." So yeah, there have been people that are close to me that have found out that they're just a little bit colorblind because they've told me that they cannot see color in the aurora. And that does happen. So on to aurora photography. I'm going to speed through this because I don't want to take up too much more time. I think I'll just go another 5 or 10 minutes and then we'll leave the rest for questions. But on a smartphone, it's pretty easy. You just kind of hold it up to the sky, use your night mode, take a tripod if you can. On a DSLR mirrorless camera, shutter speed 5 to 10 seconds. The aurora is pretty bright, actually. I know for Milky Way, you're looking at 10 to 30 seconds, depending on your focal length. Well, you can use the same lens for auroras, but the aurora moves. So you don't want to blur it out too much, and it's pretty bright, so you actually don't need that long of an exposure. Aperture, lowest f number, always. That's kind of, unless you have a really, poor lens with bad aberrations wide open, you might want to stop it down, then maybe, half a stop or a stop. in your ISO, just whatever works, whatever makes the image bright enough, doesn't really matter these days. But it's tricky, right? Milky Way photography, astrophotography, all these Milky Way photographers, I envy them because, you can use photo pills, you can use Planet, whatever, I don't know, Stellarium, right? These softwares to get your shot just right. I mean, you can drive out there, you've planned this shot out for months, and the Milky Way is right where you expect it to be. As long as you don't have clouds, your shoot goes great. With the Aurora, if you're underneath the Aurora oval, all of a sudden it's to the north, then it's to the south, now it's to the east, now it's overhead. It can be, pretty challenging. In the Aurora, I mean, you can cover, 6 or 7 stops. If there's a really big substorm, like this is 1.6 seconds at ISO 640, and this is blown out. I mean, this is a raw file, right? And before I was at 20 seconds and I was at ISO 6400. So, it's crazy. So you have to be on your toes, and that really makes it hard. So I always tell people, try and use, or just, auto ISO works for the most part. And you can keep your shutter speed the same then, or just be okay with cranking down that shutter speed when you start to see things get brighter. And, be okay with moving your camera too. Time lapse is kind of a nice way where you can mitigate some of this stress. So this is just one of the videos. I'm just gonna skip forward a little bit. I was in Fort Yukon for 3 weeks. I saw auroras, all the time, and I brought my 3 cameras with me, and I shot about 50,000 photos and compiled them into this sort of Aurora time lapse movie. I really need to do another one of these. I have probably 500,000 Aurora shots I have not edited right now, which is pretty crazy. But it's nice when you're taking a time lapse. You can just set your camera, facing one way. If you get your settings right, you don't have to worry about them, and then you can just enjoy the show. And with time lapse, the trick, hold on here, there we go. Okay, let me just back up. Time lapse, if you're not familiar, I'm pretty sure we all know what it is, but you're basically taking a bunch of photos, and then in post-processing, you're speeding those photos up to a video playback rate. So whether that's 24 frames per second, 30 frames per second, or 60 frames per second, you're basically, let's say you take a photo every 5 seconds, when you speed that up, you're going to see life move by quicker than how it actually did, right? It's a time lapse, the lapse of time. And why is it worth the extra work? Because it is a lot of extra work. You have to leave your camera out there. You shouldn't really move it because you want to get enough frames where you have, at least a 5 or 10 second video. And, you have thousands of shots potentially that you need to edit. So what's great about time lapse is that you can show the evolution of the Aurora. It actually does move. It's not just this static thing in the sky. A lot of people think the Aurora just sits there, doesn't do anything. It's just like a cloud. No, it does move, as you've seen. And you can choose sort of the best frame. You don't have to worry about capturing the moment, right? Your camera's always running. And the best thing is you can just relax, not have to stress out about moving your camera all over the place. To shoot an Aurora time lapse, underexpose a little bit. I think that's sort of just a safety blanket. Use auto ISO if you have a newer camera. We can go over this later too if you want more sort of nuanced explanations, but auto ISO works for the most part. And then pick your shutter speed based on how long you want your final clip to be, and sort of, how active the Aurora is. Lowest F number as always, and auto ISO works for the most part. Most cameras are good enough these days where the meter is smart enough to make the decision. But if you have an older camera, you might just want to use, you just want to shoot manual mode and then underexpose if you can. So here's my workflow. This is sort of my specific take on it. There's different things you can do. I have a little guide on my website that goes over all this, but I use LR time-lapse, so that's Lightroom time-lapse. It's free, and then I plug everything into Adobe After Effects. So Lightroom and Adobe After Effects are not free, so you need the Adobe suite for this, but Lightroom time-lapse is the standard software for editing time-lapses. It basically makes it so that you can smooth over, like if you're taking a sunset to Milky Way time-lapse, of course, your settings at the beginning and the settings at the end are not going to be the same. So the question then is, well, how do you make sure that that transition, right? You're changing your shutter speed, your ISO, maybe even your aperture. How do you make sure that transition's smooth? Because otherwise you're going to be seeing these big jumps in exposure. And LR time-lapse does that. It calculates these transitions based on keyframes that you can pre-assign in the software. So real-time video is what I'm really into now. I don't really shoot a whole lot of time-lapse anymore. I have 3 cameras, but I really only use my A7S III. and it's pretty much the king of real-time video, and it's awesome. Clear aperture matters though, so you start to get into the limitations of optics pretty quick, and you just buy whatever you can, which has an f1.8 or f1.4. So if I see an f0.95 anything, I just immediately add it to my cart, because I mean, you definitely notice it. You know, if I can use ISO 16,000 or 20,000 versus 50,000, I mean, that's a huge difference. So this clip, this is a really bright aurora, and it was also during a full moon, or relatively full moon. So this is like ISO 6400, but sometimes I'm at ISO 128,000 and I have to clean that up. So I use Neat Video for that, which is a great plugin for After Effects and other and basically some other software too. I think it works with DaVinci Resolve, Final Cut Pro. But yeah, if you want to do real-time video, there's a lot of different cameras that can do it now, but a really good way of getting into that for not much money is just to buy a Sony a7S on eBay for 600, 700 bucks and slap a Rokinon 24 f1.4. You can get a pretty good real-time rig for under $1,000 that way. You don't have to buy an a7S III or any of these fancy lenses. It really, and you're working with a 4K file, right? It's not that high resolution, so you can get away with lenses that are not perfect. Like, I have a 35 millimeter f0.95 lens that has some crazy coma at f0.95, but because it's only 4K, right? It's 3840 by 2160. That's 8.3 megapixels. You don't really see that, right? The pixels are so big that it just smears out all the aberrations. So you can get away with a lot by using just a cheap lens. But the camera body, it's actually funny because usually the lens matters more than the camera. In this case, there are just some cameras that can't really do real-time video, but your iPhones can. The new iPhones can do real-time video pretty well. So I think I'm just going to stop here. I have a lot of show and tell. I've seen tons of things, right? I've been chasing the Aurora for years. I've lived in North Dakota. I live in Alaska now. I've been to Churchill, Iceland. Yeah, I've seen a lot of things. I haven't seen it all, and that's what keeps me going, is that I always talk to an old timer and they're like, oh yeah, that Aurora we saw last night doesn't compare to whatever storm in 1990 whatever. And I'm like, okay, so it gets even better than that. That's pretty encouraging. And I think that's just the takeaway, is that even me, I mean, I am obsessed with this stuff pretty much, but it does change every single night. It's not the same. I think once you see one Aurora, you've only seen one Aurora. And with astrophotography, the Milky Way is the same every single night. So the Aurora is kind of a nice refreshment from that. It's like, you look up at the night sky and it's completely different from one night to another. So yeah, that's it. Hope you enjoyed this, and we can run through some of the questions. I already see the chat's full of notifications, so we will get to it. Thank you.
Thank you, Vincent. Thank you, thank you, thank you. If you will unscreen share.
Sure thing.
And I will then do this and try to do this and do this with standby from beginning, and I'm going to go, we'll go standby. Maybe not. Here we go. So, Vincent, I have a kickoff question, and we have some other questions in the chat room, and that is, our sun, a wonderful star that it is, emitting these solar storms, also has an effect on our neighboring planets and the auroras there. Can you touch on that a bit?
Yeah, of course. So to get an aurora, you need a magnetosphere and you need some sort of atmosphere. So that means that Venus is out because there's no magnetosphere. So there's no aurora on Venus. Mercury actually has aurora, believe it or not. There's a very, very, very thin atmosphere on Mercury, and there is a magnetosphere. So it gets slammed because it's so close to the sun. Earth obviously has auroras. The moon does not. Mars does. It's very strange aurora. It's sort of this glow And then they have like really small, it's really small discrete auroras because there's crustal magnetic fields. So really, it's almost like little islands of magnetospheres. There's like little bubbles, like protective bubbles. So actually, if you were to send astronauts to Mars, you might want to settle in a colony under one of these little protective domes of magnetic field. Jupiter has amazing auroras. You can see them, on Hubble, and that's because the magnetic field is so strong. And Jupiter also has moons that are spewing out like sulfur dioxide and all sorts of weird chemicals, which create really strong magnetic fields, really dense plasma. It's just a crazy plasma environment. And then all the rest of the gas giants also have auroras. Uranus is weird because, of course, the dipole axis, like the tilt axis, is completely different from the magnetic axis. So, and a lot of these magnetospheres of other planets are not perfectly dipolar either. Like Earth's is pretty dipolar. It's like 80% a dipole, and then, maybe you've heard about like the magnetic pole wandering or like this magnetic pole shift. You can take the magnetic pole, then you can take the geomagnetic pole, which is if you were to turn Earth into a bar magnet, where does that fall versus like taking all the different components of the magnetic field, where does that one pole fall? But there are some magnetospheres that are totally like random, like they just look like just a mess, like a tumbleweed or something. So like on Uranus, you get auroras just popping up all over the place because its magnetic field is all over. Saturn, of course, has auroras too. And there's auroras on some moons as well. Jupiter, Io has auroras, and there's aurora on Titan as well, one of Saturn's moons. Yeah.
Super. We have some comments and questions on chat, and let me start off with a couple. One is, and I think you kind of touched on this, the cycles of activity on the solar storms. The comment from Mumbo is, the sun is currently very active. What causes the cycle of solar activity?
Yeah, so I mentioned that there's a cycle, but the actual cause of the cycle, I'm not an expert on solar physics or the solar dynamo, but essentially what happens, is the sun is not a solid body. So when you have like a liquid body or something that's not a solid, if you start spinning it up, actually the equator will rotate faster than the poles. It's called differential rotation. That's the sort of sciencey name for that. So the sun has a magnetic field. So as it rotates, this magnetic field rotates with it. But because different latitudes rotate at different rates, the magnetic fields start to wind up, and eventually they just like bunch up and just pop out in these sunspots. So, over the course of 11 years, they'll start out nice and orderly, and then they kind of wind up, they pop out, and then they kind of unwind. And all that happens in 11 years. So you have solar minimum, then maximum, where you have all the sunspots, and back to minimum. So if the sun were rotating faster, actually, you would just have a shorter solar cycle. So that's called the stellar Rossby number, and you can actually measure that. Other stars, you can measure the rotation rates of other stars, and we've done that, and we've actually, it's really interesting. The sun is kind of an outlier when you look at other stars in terms of its solar cycle and how long it is, and models have not been able to reproduce the solar cycle. And even just like with basic physics, we cannot get 11 years, and we can't get the migration of the sunspots from high latitudes to mid latitudes, this sort of butterfly. It's called the butterfly diagram. If you plot out all the sunspots over time, they sort of form like a butterfly with the wings starting at the very start of the cycle, and they gradually move towards the equator. It's really cool. I mean, this solar dynamo is really complex, and it's it's just fascinating. So yeah, I mean, it all boils down to the differential rotation, and the magnetic field is kind of winding up and then winding down. But when you really kind of dig into it, it's still a mystery, really.
Question from Sue. She's wanting to know, do the auroras look as bright in person as they do in the pictures that she has seen?
Yeah, I mean, that's the age-old question, right? I mean, that's the evergreen question. And especially now on social media, everyone's just thirsty for clicks, and you'll get people that will oversaturate their photos. In my opinion, it's all subjective, right? But I think there is a point where it's like, okay, now you're just, it looks like it's toxic green, right? This photo that you're seeing on the screen, this was photographed in January of 2023. Even though it looks like a pretty bright aurora, this was actually quite a long exposure. I think it was like 20 seconds. So the aurora was pretty dim actually to the eye. I could barely see any color in that. So, you know, it sometimes helps if you ask a photographer, like, what was your exposure on that? Because if it's like a 1 second exposure, you know the aurora was really bright because you only needed 1 second. So I showed a photo earlier of that big spiral and it was blown out and it was 1.6 seconds. I could 100% see all the greens in that. And it helps when there's a little bit of a full moon as well, because, you know, I talked about your cones needing a little bit of light to activate. Well, the full moon can provide that sort of stimulus to activate your cones at all times. So even with really dim aurora, you can see the colors in it. And I would say I'm pretty sensitive to the greens, more so than most people, which is fortunate because, you know, this is my thing. But you know, I've been out next to people, you know, who are my age, who have just never seen the colors, even when I'm, you know, literally saying like in the moment, wow, look at those greens, look at those reds. And then of course, as you age, right, your rods and your cones slightly deteriorate. So like I've been out with my parents and they're in their 60s and they cannot see the colors. So everyone's different. Everyone sees colors differently. And, you know, you could definitely see the colors though, if the aurora is bright enough and under the right conditions that you see in the photos. It can look that green. And especially if it's a new moon, so there's not any moonlight and the aurora is really, really bright, you can actually see the green in the aurora reflected in the snow. And that's really cool. And
You're
I
making
remember
you're making me feel good because when I was up at Churchill, I could see the green, and I'm now
Awesome.
80. I'm now 80, but be that as
Wow.
it, hey, Vincent, Neil
Yeah.
is asking the question about the Carrington event.
Yep.
How it would appear in Aurora terms if it happened again.
Yeah, so the Carrington event, I'm gonna forget the exact date. It was in 1859, September or October of 1859, I think.
What is it?
Yeah, it's one of the largest solar storms we've ever seen. So it's the most famous for sure. There actually have been, this is important, there have been stronger since the Carrington event. They're just not as widely known. So there was a big one in 1872, I believe. There was a big one in 1929. Somewhere in those years. But the Carrington event was a huge geomagnetic storm. So if we're thinking the KP scale, I mean, it would have been maxed out at a 9, right? So the May storm was a 9 as well. So that's the problem with the KP, is it only goes up to 9. What do you do? Like, you know, if there's a hurricane, it's a Cat 5, but it's the size of the Earth, it's still a Cat 5. It's just a really strong Cat 5. So the May storm, which we had last year, the Gannon storm, that was a KP 9, but it was about the 10th of the sort of severity of the Carrington event. So we measure geomagnetic storms on the DST scale. It's just one more number to worry about, right? The May storm came down to minus 412. And the Carrington event, I guess it was about 4 times, because the Carrington event came down about minus 1600. So lower equals more strong. And the effects of that, I didn't really talk about the effects of space weather, but during the Carrington event, there was so much energy flowing through the ground from these currents that they traveled up into telegraph wires, and people were able to turn off all the power to their telegraph stations and send messages as if everything was plugged in. There was just so much current in the air and in the ground due to the aurora overhead. And the sparks from Morse code, you're tapping together these plates. The sparks were so great, so large from just tapping out these messages. It started telegraph paper on fire and burned down quite a bit of stations. Auroras were seen as far south as Hawaii, Cuba. Back then we didn't have cameras, so it's hard to say what that would look like now, because the May storm was seen from those places too. But we had cameras, so you could see the subvisual stuff. But naked eye reports in the Carrington event, I think the May event was pretty close to the Carrington event in terms of auroral visibility, actually. But in terms of geomagnetic impacts, like on the grid and society, it was very minor. We didn't really notice a whole lot, thankfully. But if the Carrington event were to happen today, I mean, who knows what the aurora would do, right? Every single solar storm is created differently. But you could see the auroral ovals move over latitudes like Minnesota, Wisconsin, Michigan, maybe even as far south as like Colorado, Iowa, Idaho, Oregon, places like that. And then during big substorms, see the aurora as far south as like the Yucatan Peninsula, maybe even like Panama, very close to the equator, basically. So
Keith, is asking the question, the initials STEVE. What is that?
Yes. So Steve, strong thermal emission velocity enhancement. It is not an aurora technically. Auroras are produced by particles raining down into the atmosphere, colliding with gases and releasing light in specific colors. Just like you have H alpha, that's a specific emission line, just like the aurora has specific emission lines at like, for example, 6308, 630.8 nanometers, 4278, 427.8 nanometers, 577.6. These are all specific emission lines due to the chemistry going on. But with Steve, you have a white emission, which means it's all the colors at once. It's broadband, it's continuum. And that's because it's not actually precipitation. It's not a chemical reaction. It's a hot flow of gas that's creating, it's like heating up an iron in the fire. It glows white hot. It's the same thing. It's superheated gas flowing in the upper atmosphere. And it typically forms after geomagnetic storms in the recovery phase of substorms. And it's, it could be seen from mid-latitudes like North Dakota, Minnesota, Wisconsin. It can also be seen fairly north as well if it's a really small substorm. But it was, it's been around for as long as Earth has had a magnetic field, and we've had auroras, but it wasn't really noticed until recently by citizen scientists in the Alberta aurora chasing community. And they named it Steve based on a movie called Over the Hedge. Not going to go into the story, but yeah, it's really cool because it just shows like the power that ordinary people and aurora photographers can bring to science. Like scientists didn't really know about this. It didn't have a spotlight on it like it does today, but aurora photographers went to the scientists and said, hey, what's going on here? And people collaborated and named it Steve and found out all sorts of weird things about the aurora. So
Jennifer is asking for clarification. So the color of the aurora, are you saying that it depends upon the type of gas in the
Yep.
Earth's atmosphere that's being excited by the charged particles, electrons, and the altitude as well?
Yes. Yep. So N2 plus gives you a blue emission. So a lot of these emissions are produced by, electrons coming down from outer space. They knock out a valence electron in one of these, ionic species, one of these, atomic oxygen or like N2 plus or N2. It's either, there's two processes, right? There's ionization or there's, excitation. So basically, regardless of that process, you get a photon of light emitted in a specific wavelength corresponding to the species of gas that was, affected. So like N2 plus will give you this blue emission, and like atomic oxygen O plus will give you a bunch of red emission lines, and then N2 plus into O plus, there's kind of a different reaction, kind of a two-stager. That gives you the green emission. N2 will give you this purple kind of pink emission. So yeah, all these colors are produced by chemical reactions. So it's chemistry. So, if you want to study aurora, you have to have a little bit of everything, space physics, plasma physics, some quantum mechanics in there, chemistry, like everything, right? And then I see one about the different shapes as well. And that's a little bit more complicated. If we talk about what the aurora looks like from a mid-latitude perspective, you're usually looking into the aurora. So you're seeing the aurora oval kind of as a 2D sort of view, right? It's almost like looking at a TV screen. So you're seeing everything kind of flattened together. So you're kind of looking into all these arcs and all these different forms, and you can see that, rays of the aurora stretching up really high. Now, if you're underneath the aurora oval, you're seeing these things, but you're right underneath them. So it's a little bit different of a view. So there's not only a perspective, but actually what's happening with the aurora and like different spirals and different ribbons and pillars and stuff. It really is complicated, but I would say that, this is a good question because the scientific community doesn't even really know how to explain this, even in like a scientific way. I'm not just, trying to find the words because we really just don't know. But there are certain shapes in the aurora that correspond to the same shapes in outer space. So imagine, I've been using this analogy more of like, imagine you have like a puppet master kind of controlling puppets with strings. You can see the puppet, right? It's dancing in front of you, whatever. But all those movements are going on because of somebody, up above actually controlling the things. And that's kind of what we're seeing with the Aurora. We're seeing what's actually going on in the magnetosphere in outer space with all these magnetic fields. It's like if you're plucking a guitar string, you're seeing the effects of that in the Aurora. So, I like to say there's clouds in outer space are raining down Aurora particles, and the shapes of the clouds kind of correspond to the shapes of the Aurora, but there's individual shapes which correspond to certain phenomena, but overall, a lot of it is just like kind of random, like, just like activity, right? People just kind of use that word to describe things.
I'm guessing that historically, since we have been on this planet, members of our species seeing the aurora have come up with all kinds of explanations as to the spirits and the gods who were punishing them or entertaining them. But that's another lecture altogether. The historical references that people come up with regarding our cosmos and how it influences our lives. Vincent, you have been phenomenal. I'm going to ask people in the audience at this time if they have some other questions to unmute their microphones and throw a couple questions your way. Let's see if we have anybody. Hearing none. So
Vincent, I'm located at the 45th parallel, roughly.
Nice.
And so we watch Space Weather Live pretty actively because it gives us a pretty good indication of what to expect. And if the BZ is heading negative, we grab the camera and head out. Last year was absolutely incredible. May the 10th and October the 10th. Undoubtedly the two best auroras I've ever seen in my life.
Awesome. That's awesome. Yeah.
The October one, for the first time, I saw a bright orange
Wow.
aurora.
Yeah. Yeah, I was up in Alaska for the October one, and we had clouds, but actually, the aurora oval was so far south that we were getting some weird, like these big geomagnetic storms just generate some really odd auroras, which always have me puzzled. But yeah, I was in India for that May storm, and I was just so surprised I saw it there. That was really weird. Yeah, I mean, I have a bet with people, like a $1 bet that we'll see another May event sometime in the solar cycle. So let's just cross our fingers.
The October the 10th one, what was insane about it, I'm used to pointing my camera northward to get the aurora. You could have pointed your camera 360 degrees. It was all around. And directly overhead, it looked just like a tie-dyed t-shirt.
Super. Ladies and gentlemen, once again, we express to you, Vincent, our appreciation, and on the screen is your website that everybody can, of course, copy down and visit. Vincent, on behalf of the entire organization and everybody here tonight, thank you very, very much, my friend.
Stu, I've got a question. My mic is muted. I apologize.
Go ahead.
Okay, my sister and brother-in-law are going to Norway this month. What are the chances of them seeing a decent aurora there?
Yeah, I mean, I would have to know where they're going and how long they're going and where they're staying, like all these things. But
Yeah.
I would say, what I tell people about Fairbanks, and Norway's different, right? Like if you're staying near the coast, it's a little bit cloudier. There are areas which are further inland which have much clearer skies. When it comes to going to the auroral oval, right, you have a 100% chance of seeing the lights every single night. It's all about, it's all about cloud cover for the most part.
Right. Okay.
I mean, of course, there are some nights that are better than others too. Like there's 100% chance of seeing something, and I always say something in quotations. It could be really minor, really weak, but
I think they're staying there for about a week, but I'm not
okay.
sure.
Yeah, then pretty good chances.
Yeah. Okay. I'll tell them to watch the weather, the cloud cover, go out on a clear night. And be prepared to stay out for quite a while to see anything good.
Sounds good. Thank you, Don. Vincent, again, thank you very much. I have a couple more announcements, so you can stick around if you wish to see what we're up to. All right, ladies and gentlemen, once again, PAS, the Phoenix Astronomical Society, is asking you a question. Do you have a telescope? And do you know how to use your telescope? Do you know the night sky well enough to talk about the objects that you look at? If you do, guess what? We have a job for you, a paying job for you. The Phoenix Astronomical Society has individuals who, through our organization, are contacted by elementary school teachers, Boy Scout groups, Girl Scout groups, Brownies groups, corporate conventions. They want to know if we have somebody who has a telescope and can bring the telescope to their event, whether it's a STEM classroom event at a local elementary school. We were at 3 elementary schools just this past week. If you have those skills, you need to contact Star Tours at PASAZ. They are looking for individuals who have those skills to be available to provide presentations locally here in the Phoenix metro area. Star Tours, fun activity. Okay, February night sky, got a couple things going for you. Meteor showers coming up on the 8th. That would be Saturday night. And on the 16th, Venus is going to be really bright. She's my ex-girlfriend. I dumped her because as you all know, she's second planet from the sun. She's got tons of clouds around her that reflect the light. That's why she's so daggone bright. But those clouds emit sulfuric acid. I can't take her to the prom if she's crying sulfuric acid. So I dumped her. But anyway, February 16th, Venus, very, very bright. And then on the 19th, some of you guys are into deep sky objects, and I thought I'd show you one that you might want to take a look at on the 19th. It's Bode's Galaxy, MS-81. And take a look. It's going to be rather easy for you to find. It just takes a little while. Here's where it is. In the constellation Ursa Major, the Big Dipper. They call it a plow in England, and it requires a telescope to see it. So don't think you can do that with your binos. Once again, those are 3 key dates for you for February for the night sky. And now I have a special treat for you again. If you have your camera available, take a picture of this link. SpaceTourismGuide.com has listed lots of places for you to visit. Arizona has tons of sites. We are famous for our dark skies, but of course, Vincent, nothing close to Alaska where you are, my friend. But we try. As you mentioned, the Grand Canyon can get to a border number of 2 or 1. But stargazing-arizona/, you got to copy down that link on your cell phone or write it down now. It is a great reference resource, if you will. That's kind of redundant, of places to go and things to do in Arizona as it relates to that which we love, the hobby, astronomy. So take a look at that. Hopefully you got a picture of that link and we'll use it to your heart's delight. Okay, we mentioned this before the meeting began. This club, this organization, receives donated telescopes. We do 2 things with these donated telescopes. We make sure they're operational and we loan them out to members of our organization for free for a month. So if you don't own a telescope, you're thinking about getting a telescope, you want to try out a telescope, contact us at telescope@pasaz.org. This is a loaner program. So we get donated telescopes and we use them in our loaner program. But then you'll be so proud if you are a member of PAS to know this. Other telescopes that are donated to PAS, we make sure they're operational. We turn around and sell them to our members. We look at the current street price of these used telescopes. We reduce it to almost half of the going price, sell them to our members. But we take the money from the sale of those telescopes and turn around and award $1,000 scholarships to students studying astronomy at the local community college. And this year, your organization actually gave out 3 $1,000 scholarships. We gave out a $1,000 scholarship in January of last year, and then again in September of last year, we gave out 2 $1,000 scholarships. So The Loaner Telescope program is alive and well. If you're interested in borrowing for free, you have to be a member. Contact telescope@pasaz.org. Okay, we have some upcoming events. As mentioned, we have telescope workshops. Operating and or buying a telescope, February the 20th, 7 o'clock. You need to register. We require everybody to register for our events for one major reason. More than half of our events depend upon Mother Nature, the weather. And if the weather goes bad, we will tell you, but we can't tell you if you don't register and give us your email. So, same thing goes for the telescope workshop. We want to make sure we have instructors available for you should you come, or if it has to be canceled for an emergency reason. So the first telescope workshop, February the 20th, 7 o'clock. Go to www.pasaz.org to register for that event. Star Party. As mentioned before tonight's meeting, last Saturday, we had 23 telescopes and almost 55 people showed up for our Star Party. This is a fun event. This is where telescope owners have a chance to, number one, set their telescope up and talk to other users of telescopes to find out what their gear is, how they use it, etc. I would recommend that you line yourself up for that telescope Star Party, excuse me. Now, the next lecture is Thursday, March the 6th, and we will be having Vanessa Grithieu. He's going to be talking with us about Kitt Peak National Observatory. Arizona location. If you're interested, you need to sign up for that lecture as you did for this evening's lecture. Once again, we start at 7. You can register by going to www.pasaz.org. We got another telescope workshop on the 20th, again, 7 o'clock. Whether you're thinking about buying a telescope, or if you have a telescope that you don't know how to use, your wife bought it for you, your husband brought it for you, and you say, holy cow, this is a lot of work here. I got to learn how to do this. And the manual isn't helping me. You need to contact us at www.pasaz.org and see if you can sign up for an available slot at the March 20th telescope workshop. You need to tell us what your telescope model is so we have somebody who knows how to instruct you on its use. And then we have another Star Party, March the 29th, 6:30. Once again, this is where people bring their telescopes, set them up, and then we just view. As with all of our events, please use the link www.pasaz.org to register. Board of Directors. You have 10 people who are not paid, who try to keep this organization operational for you with lectures, workshops, star parties, etc. And we have a monthly meeting of the board, 7 o'clock, and we try to design, etc., events that are pleasing to you. And if you have some concerns, questions, complaints, here's what you can do. You can send them to me or any board member at that address, president@pasaz.org. Ladies and gentlemen, as the slide before you says, thank you very much for your continued support of our society. We hope we're meeting your expectations. We've just finished another wonderful year. We've increased our membership, and we're having more and more events, and more people are showing up to these events. And as our lecture shows you tonight, Vincent Ledvina has given all of us a reason to continue looking up at the night sky for the Aurora Borealis or the rings around Saturn or whatever you want to see. It's all up there. It belongs to you, and it's free. Ladies and gentlemen, thank you very much for joining us this evening, and it's time for me to say good night and clear skies.
Thank you so much, Stu. Take care, everybody.
Thank you, Vincent.